physics question time. Tiny jumping humans. So there was this Veritasium video about a Google question, an interview question, where you're trapped in a blender and you're a super tiny human, and how do you escape? And apparently the answer is you just jump out, because the idea is that small humans can jump just as high as normal sized humans. And it kind of makes sense, right? Because if you think of like a dog, dogs can jump about as high as a horse. I mean, horses are taller, but dogs can jump really high, and they're smaller. So let's show this. It's not quite true, but it's kind of true. So let's just do it. We got some calculations to do, and hopefully we'll model this in Python. That's my idea. That might go bad, but we're gonna do it anyway. Okay. So the first thing we need to do is to model our human. And so I'm gonna model a human as, let me draw my human. Now you would say, hey, assume the human is a sphere, but I'm not gonna do that. I'm gonna assume the human is a cylinder. Now my jumping human cylinder has some parameters that we need to deal with. So first of all, we have the height, right? So a normal human would be 1.75 meters or something like that. Now our human has two other really important properties: the radius r, and then I'm gonna say this s. S is like when you jump, you have to squat down and jump, because all those properties will change. If I make a human that's half the size, right here, or even smaller, I'm going to assume same ratios of parameters, same ratio of radiuses to the height and the squat distance to the height. And then I'm going to make some other assumptions too. But when that smaller human jumps, I'm going to assume that they have some force that pushes them up, they have a mass, and then we can model how high they jump in that particular case. But we need to look at jumping humans anyway. So let's just start off with this jumping human model. I'm going to erase that. We'll come back to the human. Because what I need to do is to get an expression for the force that this person applies while they're jumping. And so if you think about a jumping human, we can break it into three instances. The squat distance, they're squatted down like this, you can't even see me, and then they jump up, but they're still in contact with the ground, and then they're in the air. So that's three positions. Why? One, for the center mass when they're squatting. Two, Y2 is when they're just leaving the ground, and then 3 is at the highest point. Okay. So we can convert those over to our other things first, but I need to get an expression for the force, because what's happening is while they're jumping, they're pushing on the ground and the ground's pushing on them, and that's what makes them go up. And then when they're going from here to there, it's just the gravitational force. And I want to find that force. That's what I want in terms of these things. So in this particular case, you could say, okay, I'm going to use Newton's second law or the momentum principle. I could say F net is delta P delta T. And I can draw a force diagram at some point. I have the force of the floor, I have the gravitational force, and then we could do something there. However, the momentum principle, Newton's second law, those are really the same thing. They depend on time. And in this diagram, we don't need time. So that's not the best way to go. Instead, we can use the work energy principle. So this says the work is equal to the change in energy, where we define work as, for a constant force, F dot delta R, where delta R is the displacement of the force. Now, you may think, hey, that would work, except that when they're going from here to there, the floor doesn't move. The floor doesn't do work on the person. So you can't do this to find that force of the floor because it doesn't move. And here's where we cheat. Okay, so we're going to say, whenever you use the work energy principle, you have to pick a system. So I'm going to pick the system of the point particle system of the person. So there's two types of systems you can pick. You can pick the real system of the person, and the person, there's no work done by the floor, but there is an internal energy. So when you jump, you would decrease in internal energy. That's why you eat Wheaties in the morning for breakfast, so you have that energy to decrease. If we assume that the person is a point, then there is no internal energy, there is no potential energy. All you have is kinetic energy. But now, instead of doing the work done by the force and how far the force moves, I can use the displacement of the center of mass. And so that's what I'm going to do. So let's think about this person going from y1 to y3. And so the only type of change in energy is going to be the change in kinetic energy. That means I'm going to have two works, right? I'm going to have the work done by the gravitational force and the work done by the floor. And then, of course, we define kinetic energy as 1/2 mv squared. But it doesn't matter, because if I go from point 1 to point 3, v1, 0, v3, 0. The change in kinetic energy is 0. Starting like this, ending at the highest point, 0 change in kinetic energy, because both of those are 0, so we don't have to worry about it. So that means that we have this. Work is going to be, I'm going to call this work done by the gravitational force plus work done by the floor, and that's going to be equal to 0. That's it. Okay, so what's the work done by gravity going from 1 to 3? So that's going to be equal to, I'm going to put 0. The work done by gravity is going to be the gravitational force, mg, and we're only in the y direction now because energy is a scalar, so we don't need to worry about that. Mg times the displacement, which is going to be y3 minus y1. That's how far the gravitational force applied, and that's actually negative, right? Because the gravitational force is this way, we're moving that way, it's negative work. Now what's the work done by the floor? The work done by the floor is going to be that force, I'll just call it F, times this. It didn't move, it didn't apply a force all the way, it only applied it from 1 to 2. So this is going to be F times y2 minus y1. And that's it, and that's equal to 0. So this isn't so bad, right? All I have to do is to add that to both sides. I get F times y2 minus y1 is mg y3 minus y1. So F, running out of room, I'll put it at the top because we're going to have to rewrite this. So F, this is the force the floor exerts on the person, is going to be the mass of the person, gravitational field. Is that too high? No. y3 minus y1 over y2 minus y1. And you'll notice right away we should check some things, right? Does this have the proper units? Well, mg is going to be units of force times distance over distance, so I do get units of force. That's good. Okay. Now I want to use this in my model of a jumping human. So let's switch back over to, we don't care about that anymore. Let's switch over to our human model. So here's the ground. Here's my cylinder. And like that, and I have a height h, and then I have this s, and then I have r for the radius. How do we convert these to those, right? So when they squat down, maybe I should draw this like this. H is the total height, but this would be the squatted distance. So this is going to be h minus s. And then we're going to be right here to h, and then we're going to be up here to the highest point. And I'm going to call, we're talking about jump height. How high did they jump? Not how high did they end up, right? So this distance to this distance is how high they jumped, right? If I have to measure the change in height for a jump. I can't just measure how high I get. I mean, you could, but that's not what I'm going to do. Okay, so over here, y2 minus y1 is s. But what about this? What's this y3 minus y1? Well, this is y, and the extra distance is going to be s, right? So this is going to be y plus s. and that's my jumping force. Okay, and I want to know, I want to solve for this y. But let's go ahead and think about this in terms of changes in human size, right? So if I make the human smaller, the mass is going to change, and S is going to change, and S is going to change. And F is going to change too, right? Because a smaller human is not going to apply the same force. So that's the first thing. We need to get an expression for F for our smaller human. So we're going to make a couple of approximations. I'm going to write them down over here. Rho equals constant. And I'm going to say it's 1,000 kilograms per cubic meter, right? But a smaller human has the same density. A smaller human has the same ratios of sizes, the same proportionality, and a smaller human has a force that's proportional to a squared, the cross-sectional area, right? Because muscles, if you make a wider muscle, it's going to be stronger. So I'm making the assumption that the jump force is proportional to the area. So that would be equal to, let's say, F is C r squared, where C is just some constant, and we'll find that out later. And then, so finally we need to get S and R in terms of H. So let's just say S equals A H, and then R is equal to BH, right? And those are just some fractions, some ratios. And we can pick whatever they were, but we can't pick anything for A and B because we want the density to be constant. So you can't just pick whatever you want, but it doesn't really matter for right now. We'll pick those in a little bit. So they should be some fraction like 0.5, 0.2, whatever. So let's go ahead and put all this stuff in. So now I have F is going to be C r squared. M, the mass, is going to be the density of the person, rho, times the volume, which is going to be pi r squared h. Y is y. S is going to be plus AH, and then all of that divided by AH. Now I can get R in terms of H also, C, and then I'm going to have B squared H squared, rho pi B squared H squared H, I got another H, Y plus AH over AH. So we can just start canceling. We want to solve for y, but we see that some things cancel. B squared, H squared, H squared. Oh, there's a pi. There's a pi here. Well, you could drop the pi in there with it, but let's do that. So there's a pi. Just to get rid of that one. So now I have C equals rho. Oh, cancel. That's nice. Rho times, oh, there's a G here. Forgot that G. Rho G Y plus AH over A. So now let's just solve this for y. So rho G Y plus AH equals AC. Y plus AH equals AC over rho G. So y is going to be AC over rho G minus AH. And you see here that the height does not completely cancels. Most of the height cancels, but it doesn't completely. And now it really depends on what you'd mean by how high they jump. If you want to go from squatting distance to the highest point, then that h wouldn't be there. Okay, y3 minus y1, if I got rid of that, I wouldn't have that h term in there, and this would be exactly the same. So it's not quite true. But there you go. So this actually says taller people don't jump as high, right? So if a taller person doesn't jump as high, but they can still end up higher. They can end up higher because they start higher. This is the change in height from their center mass to their highest point. So they have to subtract off that squatting distance right there. Okay, so we have it, right? We have our jumping height for small humans. But now let's go ahead and model this in Python. That's really the fun part, right? So I want to model this, and so what I'm going to do is to make a normal human jump. So if we have a normal human, our normal human, we need parameters for a normal human. So and then we can apply, because we need to find a, what happened to my B? It canceled. Interesting. We need to find A and C, right? So we're going to need to find those things. And we can get those by picking a value for Y for a normal human and then solving it. And we're going to do that. Okay. So let's say we have a normal human, H 1.75 meters. Y, how high can they jump? 0.2 meters. And you may think that's not very high. Well, I've seen myself jump, and I do not jump very high. Okay, so I'm trying to be realistic. So that's the case. Let's say rho is 1,000 kilograms per cubic meter. They're like water, right? Humans are like water. And so I want to solve for this parameter C. So let's solve that for C. So I get C, let's see, AC over rho G is Y plus AH. So C is going to be 1 over A, or this, actually it's going to be rho G over A times Y plus AH. And so now I guess I got to find A. So let's get A from our cylinder right here. So A was the term in front of the, yeah, that was this S equals AH. I just picked that. It doesn't matter. Okay, so let's pick that because that's not really changing the volume, that's just the squat size. So let's say A is 0.25, so a fourth of the person squatting down. Maybe that's okay. I'm not sure. Seems like okay. So A is 0.25, rho G, we have all the values, we can plug it in and get C. Once we get C, and we do need to find R, just for our visual model. Yeah, so let's go ahead and calculate how we'd get R. So I know I have a cylinder, and the mass is going to be 75 kilograms. I'm going to pick the mass at 75 kilograms and a density of 1,000. So that's going to be equal to 75 is equal to the density times the volume, and the volume is going to be pi r squared h. That's the volume of a cylinder. So I want to solve for r. Let's write this as a squared. No, we called it b. So I'm going to say 75 is rho pi b h squared h. So that's going to be 75 rho pi b squared h cubed. So b is going to be the square root of 75 divided by rho pi h cubed. So that's going to give me my ratio for that. So I have a 0.25, b is that thing right there, square root 75 over rho pi h cubed. So here's what I'm going to do. I'm going to start off with a cylinder, and my cylinder is going to jump. I'll go ahead and change the size of it. Okay, we can change the length of it. I'm not sure how you would do that. Okay, I'll make 2 cylinders. No, I'm going to make 1. Because as you move up, I guess I could draw the cylinder upside down. Yeah. I could just draw the human as a dot. I think, so if in Python, if we make a cylinder, we have 2 points. We have the position as one end, and then the axis is the vector to the other end. If I want to squeeze that down, I guess I could just change the length of the axis, and after that change the length of the position. I'll just do that. So I'll just have one position. So the goal here is going to be start with 2 loops. The first loop, I'm going to take my cylinder and I'm going to apply the 2 forces. So I have F is going to be F push, this is F net, minus mg, right? And then we can use that to change the momentum, and we can change the momentum, which would change the position, and we'll do that until this gets up to y is equal to s. And then they're no longer jumping, and then we'll just take away that and let it go on its own. Let's see how well this works. Okay, jumping over to Python here. I did this before, but I'm kind of redoing it, so this may be bad. Let's just start off with some properties. M equals 75. H equals, make that bigger, that's good. H equals 1.75. A equals 0.25. Rho equals 1,000. Y, let's call it Y max, is equal to 0.2. B is equal to the square root of M divided by rho times pi times h cubed. Now I'm going to go ahead and calculate the force, right? Let's call this FF. And that was C, which I didn't calculate. I need to calculate C. C equals, there it is, rho, I need G. G equals 9.8. A, I got that. Okay, so C equals rho times G times Y plus A times H divided by A. And then so now I can calculate my force. FF is going to be equal to pi times, oh, I need R. Let's just write R equals, I'm going to say R is B times H, and S is equal to A times H, just so we can talk about B and S, R and S, instead of using those constants. So it's going to be pi times R squared, and then C. Let's just print F to make sure we're on the right track. FF equals FF. See, we're not on the right track. Can't find variable y because I called it ym. Okay, 1071. Okay, I mean that. So yeah, that seems right, because if you have a person, it's greater than their weight. It's got to be greater than their weight, which would be around 750, right? Times 10, 75 times 10. So that seems okay. Okay. Now I'm going to make my cylinder. Let's just make our cylinder. I'll call it human, HU, for human. It's going to be a cylinder. Position is going to be vector 0, 0, 0. Radius is R. Axis is vector 0, 0, H, 0. And let's make it color equals color dot red, and let's just run that. You can't even see that because I'm dumb. Okay, it's nothing major. Let's see if that actually works. And there it is. There's my human. I've been using a white background lately, and we could put a ground and all that stuff. I'm not gonna do that. I just want to make a jumping human, and then we can change the size and plot it and stuff like that. Okay, so I have the force. Let's just go ahead and set some properties of hum. Hum.m equals m. Hum.p, the momentum, is 0, 0, 0. I'm going to need that. Let's see. I'm going to assign the force as a property of the object too, which is kind of weird, but it works out just fine. So hum.f is going to be the net force, right? That's the net force. I'm going to start off with the net force of the floor pushing and gravity, and then we can change that later. So it's going to be equal to C times FF times vector 0, 1, 0. So I have to turn it into a vector. So I have to multiply by the unit vector in the y direction, which is vector 0, 1, 0. Now for the gravitational force, it's going to be let's just say plus hum.m times vector 0, negative g0. So here, again, my big old face is blocking that. So here, I just want to point out, I use g as a scalar value, but in the force, I need it as a vector value, so that made it into a vector. So that's the net force in there. Now I need my time, t equals 0, dt equals 0.01. And I'm going to go ahead and define a value, y, because I'm not going to change the position of my human. I'm just going to change the axis. So let's just say y equals h for now. Okay. And so here you see what's nice. I used ym before. Now I want to jump. So I'm going to do while y is less than s. While y is equal to 0. While y is less than s, the squat height. Rate 100, so I'll make it move in real time. So the first thing, I don't need to calculate the force. I already have the force. The force is constant. It doesn't change. All I need to do is to update the momentum. So hum.p equals hum.p plus hum.f times dt. That's it. Now I need to change the position, but I'm actually going to change the y value. Y equals y plus, I'm going to do a little trick here. I'm going to do a trick called, I'm going to say hum.p.y times dt divided by hum.m. So that's a scalar equation, right? And now I'm going to change the axis of the cylinder so it looks like it squats. Oh, did I do this right? So up here, I need to start this at h minus s for the initial size, right? Because they started off squatted. So now I can change the axis. Hum.axis equals vector 0, y, 0. Now I'm going to update time, t equals t plus dt. Okay, so I'm going to run this. So we should see the cylinder just get longer. It got really skinny. Weird, what happened? What did I do? Hum.p. Oh, it just got really long. I did do. I'm updating the momentum. Let's print. Let's just print the force, and it should be positive because it looks like it's doing something weird. Oh yeah, it is. It's giant. That's why. It just got really, really, really long. Okay, so my force is wrong. C times FF. It's just FF. I already calculated F. Okay. It's getting really... Oh, I think it is fine. It's really small though. This should be Y plus S. Because we're going to start... No. I'm doing a trick here that I don't like. Okay, let's run to the board here and look at that. I want to make my cylinder start like this. And so this starting height should just be h minus s, right? That's how high it should be. And so I'm going to call this value right here, that's what I should do, I should call that h minus s and let that go until, so y equals h minus s, and then run that until y is equal to h. I think that's what I need to do. Okay. So up here I said y is 0. I need to be h minus s, and then this is just going to be y, and then run this until this is equal to h. Yeah. Huh. Oh, I didn't change. axis. Oh, this should be, so it should start off as y is h minus s. Okay. Let's just turn this off. All this for just a dumb calculation, which I could do without. Let's just see what it looks like when I start it. See, it's too tall. H minus S. Let's do this as, oh, Y, but I didn't draw the cylinder. So the cylinder is position X. I did do that. So H minus S. And while it's less than H, let's just slow down time. It didn't go at all. So while y is less than h, it is less than h. Is he even calculating that? Okay, so it is. But it's not changing it. Axis is vector y. H minus S. Maybe I should just forget that whole thing. I'm just going to let it jump. I'm going to let it jump and not try to make the cylinder look right, because that's where I get my problem. Okay, so I have my thing. I'm just going to change my cylinder. It's going to be of axis, going to be H, and then we don't need to make it too complicated. So that updates the momentum, and use the momentum to update the position. Hum.pos equals hum.pos plus hum.p times et divided by hum.m. That should work. And it's just for jumping, so it should move. Yeah, okay, just zooming out a little bit, and it's going crazy. It's never ending. Oh, because, again, I did this. Okay, while hum.pos.y is less than s. See, this is how you know it's live coding. Okay, good. Now, I can just go down here, and I can change my force, because now it's done jumping. I'm just going to say hum.f equals hum.m times vector 0, negative g, 0. That's it. And then I can repeat this stuff. And I'm going to do this just to make sure that I'm on the right track. What I'm going to do is say while t is less than 1, because I don't want to make a mistake with something weird like that. So I'm gonna update the momentum, update the position again. The only thing now is the force is different. Okay. Okay, good. So now let's just do while hum.pos.y is greater than 0. So while they're in the air. Ta-da! Okay. Now we can change all the sizes and stuff like that. I want to go ahead, I'm going to make 2 humans. I'm going to just redo the human, just for fun. So I'm going to make a graph of the position as a function of time for the jumping human, and then we'll make a second graph for the second human and redo it. And then we'll be done. So let's make our graph up here. G1 equals graph. Title equals Google jump. That'd be fun. X title is going to be equal to time. Y title is Y. And then let's make the size. Width is 400. Height is 200. And then I need I'm going to make 2 graphs. So F1 equals G curve. Color equals color dot blue. And this one I'm going to give it a label equals H. Let's just call it H. And then F2 is the second curve, G curve, color equals color dot blue dot red, and label equals 0.2H. That's gonna be, I'm gonna have 20% human. Okay. So down here, I'm just going to plot. I only have the real human so far. f1.plot t hum.pos.y, and then I'm going to plot that again in the second loop too. Okay, so this should just be one curve. So there's our jumping human. Pretty good. Okay, they jumped, they come back down. Cool. And you know, their center mass, this because it went 0.6 high. I think that's because I'm looking at the bottom of the thing. I'm not really sure. It shouldn't go that high. Oh yeah, that's from the bottom, and then that's a little strange. But let's just change the mass and let's see if we get something different. So now what I'm going to do is I'm going to copy everything from here. I'm going to copy all this stuff. And I'm going to do it again. And this is called coding like it makes sense to you. So here is the second print. So I'm going to say this is just 0.2 times. Now I do need to recalculate the mass. A is fine, rho is fine, ym is fine. I'm not going to recalculate C, right? Because that's my C value. G is fine. B, I do need to recalculate that, so I need to calculate the mass. So the mass is going to be rho times pi. Well, I calculate B first, then I calculate the mass. B. Oh, B is a constant, right? B doesn't change. B and A don't change, right? Because they're the same proportions as the other thing. Y doesn't matter. G. So now R is dependent on H, which is smaller. S depends on H. F depends on H and R, and they all change. So that's all fine. Again, I have my cylinder. Everything's the same. All I need to do is go down here and change this to F2, I think, and change this to F2. And let's just run it. So it should run it twice. And this is not the best way to do it. This is just the way that makes sense to me. That one went down. Okay, I messed up bad. Oof. What did I do wrong? Oh, I didn't reset the momentum to 0, did I? So here's P. I did. Oh, hum.m is going to be equal to rho times pi times r squared times h, which I changed. That is the second one. Okay. Okay, there you go. So almost as high, but not quite as high because they didn't start as high. So that's the thing. They didn't start as high, so they didn't jump as high. And I think what happens is this should actually end up here, and then this would be your jump height right there, right? Because they didn't really start at that distance. So, but I think overall it works. Small humans jumping, big humans jumping, about the same size. I'll put a link to this code down below. I'll put a link to the Veritasum video, which I thought was pretty good too, down below. Now, you do have homework. Now that you have a numerical model for jumping, you can do something else, which is to add air resistance. Air resistance is going to make a big difference because as you make the human smaller, the mass decreases as h cubed, right? It's proportional to h cubed. But the air resistance is proportional to h squared because it depends on the cross-sectional area. So if you make something half as small, it's going to be 1/8 of the mass, but only 1/4 of the air resistance force. So as they get really, really, really small, then that air resistance force makes a big difference. So they won't quite jump as high. But I'm going to leave that as an exercise for you for homework so that you can do that because this video is already too long and no one already made it to the end of this. You've made it to the end of this. A double high five. Talk to you later.